the University of Nottingham's distinctive Jubilee campus, a development that is intended to demonstrate the university's commitment to exemplary standards of energy efficiency in its buildings. Located about a mile away from the main university and to the southwest of the city centre, the campus originally opened in 1999 on the site of Nottingham's famous Raleigh bicycle factory, a 7.5 hectare brownfield site housing a variety of former industrial buildings. Home to the university's business school, the campus has been constructed around an artificial lake on the River Leen and has extensive enlargement plans. The latest phase of the development has seen 3 new landmark buildings constructed, structures which are intended to demonstrate the university's commitment to a wide-ranging policy of environmental responsibility.
The background to the Jubilee campus extension is to develop the campus we first opened here on the old Raleigh bicycle factory in 1999, and we're an expanding university growing with research and student numbers, and we needed new buildings to accommodate that expansion. The 3 new buildings that we see were developed to facilitate the growth in student numbers but also our interaction with industry, and we wanted them to be iconic and sustainable.
Located in a suburban area to the southwest of the city centre, the latest phase of the campus development was concentrated around Triumph Road, running north-south through the site. The new academic buildings are located to the west, and a new research and innovation park is being constructed to the east of the road. Connecting the two is a public boulevard across the site. This walkway links the campus lake, which was created from a neglected former culvert, and the surrounding area.
The university's original brief for the 3 buildings that were identified as the first sort of development phase of our master plan was for something that was very, very striking and iconic. The university sees their buildings and sees their developments as almost like a tool for promotion, not just locally, nationally, but internationally as well. So that was really our brief at the start of the project, to produce something that was very, very striking yet contextual, which sat within the city of Nottingham.
The 3 new buildings for the first phase of the expansion comprise a gateway building, later renamed the Sir Colin Campbell Building, a zinc-clad structure which spans the Triumph Road. Further north are 2 distinctive terracotta-clad structures, the Amenities Building and International House. It's on the issue of sustainability, though, where the development excels. High-performance facades work in tandem with the thermal mass of the building's exposed concrete to reduce heating and cooling loads. Glazing is kept to a minimum, and all windows are set back to shade the interior from high-angle summer sun while admitting maximum levels of low-angle winter sun. In place of mechanical ventilation, air quality is maintained using a displacement system which is quieter and more energy efficient than conventional systems. And to provide heating and cooling for the 3 buildings, a series of heat pumps extract embodied energy from the campus lakes, cooling the building in summer and providing heat in winter.
The university in its first phase of the development went for highly sustainable buildings, and we consider them to be an exemplar of higher education buildings, and we wanted to continue with that emphasis on sustainability and indeed to develop it further with the new buildings. Now this links in not only to us wanting to be good citizens, but also the fact that the university has a tremendous amount of research in sustainable design, building technology, energy research. So it links the research base of the university into the physical infrastructure that we can put up.
The ultimate goal, in reality, the ultimate goal of having such a strong sustainable agenda is not only to reduce the carbon footprint of modern developments, it's also to create pleasant working environments for the occupants. So people can come there, they feel comfortable, they're not in very hermetically sealed boxes, they're able to open windows, they're able to have a degree of control over their environments, they're able to work with a high degree of natural lighting and not work under electrical lighting. So really, to sum it all up, it really is striving to create the best possible working environment to attract the highest calibre of students and academics.
With the university's brief for the development of the Jubilee campus extension placing so much emphasis on sustainable design, it was imperative to integrate renewable energy into the project. The design team carried out a renewable energy feasibility study during the pre-planning and outline stages of the design to determine the most appropriate approach. A range of options, including wind, solar, biomass and ground source heat pumping to make use of geothermal energy, were considered.
The feasibility study was as a reaction to the university's brief. There's considerable emphasis on incorporating renewable energies into the development, and so we looked at biomass for heating, wind energy, solar thermal and heat pump system. The feasibility study looked at the energy profiles of the development, and it became clear that a heat pump system gave the most flexibility and met the criteria in terms of heating and cooling. Next question was, how are we going to actually incorporate that into the buildings? There's a number of ways it can be done with closed loops within the structural elements, using the local aquifer, and then we looked at the existing man-made lake on the site, and we investigated the feasibility of using that as a heat sink for the building.
In England, we need pretty much an even amount of heating and cooling in winter and summer, and that works well with the embodied energy off the ground and the lake. Secondly, if we design the building so that heating and cooling demands are low enough, we can offset the entire demand by using renewable energy and do away with the chillers and the boilers, so it looked like a winner.
The lake is in essence a thermal mass which maintains its heat in winter and it's cooler in summer than the air temperature around. So we can make use of that to drive the heating and cooling of the building. So we have heat exchangers which are submerged into the lake, and they drive air cooling units through reversible heat pumps which deliver hot air in the winter and cool air in the summer to all three buildings. And we have no backup system, no conventional boiler system, and we believe it's the first time anywhere in the UK that such a system has been used without any conventional backup.
Each of the three new buildings has a dedicated central plant system which houses the heat pumps. A closed-loop circuit uses water as a heat transfer medium and runs from the buildings to the lake and through the heat exchangers. During summer, the lake is used as a natural heat sink. Excess heat is absorbed by the heat pumps, transferred through the closed-loop system and deposited into the lake. During winter, the lake is used as a natural heat source. The heat pumps, which are reverse cycle, absorb heat from the lake, compress it and deliver it to the buildings. Key to the whole system are the stainless steel heat exchangers submerged in the lake. Depending on the time of year, these either accept or reject the embodied energy within the water. So how do they actually work?
The heat exchangers in the lake are very similar to the radiator at the back of your fridge. So what sits in the back of your fridge takes the heat out of the fridge and releases it into your room effectively. Now the lake is very good because the lake is more for more stable temperatures. It's a bit warmer in the winter and a bit cooler in the summer than the air around it. So our heat exchangers in the lake are just the radiator from the back of the fridge, which is deposited into the lake to make use of the better efficiencies and the better temperature differences both in winter and in summer.
Each building uses a heating and cooling strategy specific to its function in order to minimise energy usage. Delivering the fresh air internally to all three buildings is achieved via a low-velocity, low-pressure underfloor system. These deliver air into the rooms before warm stale air is extracted through high-level return air grills within each space.
In order to deliver air into the spaces, the client wanted a fairly flexible approach. We decided to use a floor plenum, so it's a raised floor which is slightly pressurised by the fresh air delivered from the central air handling plant. The air is then delivered into the space via high induction swirl diffusers, which create a very comfortable environment. Supplying the air at low level means that the natural buoyancy can be used as the air enters the space, it's warmed up and it's extracted at high level.
Low level, low velocity air supply systems work really well with the buildings that have high occupancy and have got a need for flexibility. The floor plenum is a type of system that is really good for educational facilities because they've got a lot of churn, they move stuff around and they can move the floor grills about. Now the floor grills are very important because what they do is deliver air into the occupied zone. So they deliver comfort where the comfort is needed. The air would come in, envelop the occupant, pick up the heat and the impurities slowly rise, and then we pick it up at the edge of the room, which gives us the flexibility we need to give the university what it wants.
The concrete structure of the building is designed to help heating and cooling by acting as a large thermal mass. This allows the building to cool during the day by absorbing unwanted heat gain. It's then cooled during the night using cooler evening air.
In structural terms, the buildings are quite simply designed. They are in situ concrete floor slabs placed on ground beams which are on short bore piles. The cores of the stairs and lifts are used to strengthen and give rigidity to the buildings. In terms of the two amenities building and International House, there are also steel trusses hung off the cores to support the cantilevered portions that hang out outside of the main core area.
The role of exposed concrete within these three buildings plays an extremely important role in acting almost as a thermal buffer, so that when people arrive in the morning, the building hasn't overheated by lunchtime. So the idea of the exposed concrete is it can absorb the heat generated by the computers, by the lighting, by the people within the building. I mean, the biggest problem that we have with these three buildings is overheating. It's not really an issue of keeping them warm because they're so well insulated. It's actually keeping the environment very stable and cool. So basically the concrete's collected all this heat during the course of the day. At night time, it's an opportunity to actually use to purge the building, ventilate the building, to actually cool the structure back down again so it's ready for the next day.
Externally, the highly insulated and airtight facades use optimum glazing levels and orientation to ensure good levels of daylight. By combining insulation, solar protection and good daylight, it was ensured that both winter and summer thermal loads remain low.
In terms of solar protection, the buildings are all less than 50% glazed with solar controlled glass, and the windows are set in deep reveals, which helps to protect against the high sun in summer, but also inside the shelves act as a light shelf to deliver enhanced natural lighting into the buildings.
The process of providing natural daylight within the buildings was a very, very intensive process, and again we worked very, very closely with Faber Monsell to develop this. I mean, there is an optimum, in reality there is an optimum between solid and glazed on building facades, which equates to about 60% solid, 40% glazing, roughly. But again, it has to be carefully considered in terms of the orientation of the building, which aspect that elevation is facing on. And you have to really think of it in an inventive way, because it isn't a huge amount of glazing, how you actually can utilise the amount of glazing you have to really create a pleasant, naturally lit internal environment.
It's intended to monitor the actual energy performance of the buildings, but the predicted carbon footprint is anticipated to be around 55% lower than buildings of the same type and makeup. Based on the Part L calculation method, the carbon emissions for the Sir Colin Campbell building are expected to be 47 kilograms of CO2 per metre squared annually, 53 kilograms for International House, and the amenities building coming in at around 87 kilograms of CO2 per metre squared.
If I try and compare these buildings to a similar building of conventional makeup, I think we have a very much better environmental performance, at least 50% better in terms of CO2. Of course, across the university we have a whole variety of different buildings, the oldest going back 100 years or so. And we have a very sophisticated monitoring system of buildings across the university, and we'll be looking at what the actual performance of these buildings is compared with our other buildings on the campus over the coming months and years. But we expect them to be an exemplar in higher education delivery of sustainable design.